morning. Welcome to our science seminar today. Hope you're all doing well. Hope you're staying dry. Ready for drier weather. Too wet. Before we get started today, I just want to let you know that we have a couple of really good talks coming up in February to add to the momentum of James's talk here today. And these are outside speakers, so it's nice to show a big crowd when they come in to advertise the university to them. Next week we have Sarah Bittner coming in. Sarah Bittner has a BS in chemistry from UC Berkeley and a PhD in chemistry from the University of Chicago. And she's also a registered patent agent with the USPTO. And she's going to be talking to us about the scope of claims in chemistry, which is similar to the scope of claims that you have in any other field. So if you guys are thinking of patenting your senior design project or something like that, this would be a very good one for you to come to. Then the week after next week, we have Dr. David Larry from University of Texas in Dallas, who's coming out. So Sarah Bittner is coming from Houston. David Larry is coming from Dallas. So these people are coming a long ways to see you, if they want to see you. Okay? And he has some interesting background. If I can find it here on the back sheet. There's this. Okay. He has his bachelor's in science from King's College London, and he has a PhD in computer modeling of the atmosphere, okay, from the University of Cambridge. Right? And he's coming to us from the University of Texas at Dallas. So these are two good talks that will be coming here in February. But not as good as today's talk. Because today's talk is given by one of our own, who I really don't know very well, and who I was talking to before the seminar. Why don't I know you? I know all the students that are giving talks. And he informed me that he was able to detour my general chemistry classes by transferring the credit in. Okay? So maybe that's why he's doing as well as he is today. Skip my class, that's why. Yeah. Right. Okay. Yeah. So we'd like to introduce you today James Morrison. James Allen Morrison. I guess he goes by Allen, is that right?
Yes, sir.
Okay. And he's going to be talking to us about some REU work that he did. And after the seminar, we'll be having lunch in the Joyce Room, and you're very welcome to join us to hear more about his adventures and his experience, and I hope you do. So let's give James, or James Allen.
Good afternoon. Like I said, my name's Alan Morrison. I am a 4+1 Bachelor's of Science in Electrical and Computer Engineering student here at LeTourneau. What I'm going to do today is kind of give you an overview into the inside of REU work and some work I've done here at LeTourneau. And then at the end, I'll share some opportunities to actually get into REUs and research here at LeTourneau. We'll have a little bit different perspective here today because in science seminar, you often have scientists that look to answer questions in a different way than engineers do. So engineers are all about solving problems directly through research. So hopefully it'll be enlightening for some of you, and those of you who are engineering will probably see some procedures that you've seen before. So to start off, I will talk about my LeTourneau research. So I'll read the title, it's on the slide, Determining Non-Newtonian Fluid Medium Characteristics Using RF Techniques. A lot of words, but a simple concept. This was done under Dr. Hu Kim in the Electrical Engineering Department. And it was about a year project. So, to give you a background to what I was doing here. Non-Newtonian fluids are a very special chemical substance. Whenever they are under stress and atmospheric pressure, they actually change their physical structure. So, to give an example, cornstarch is the non-Newtonian fluid I used. Whenever you slap water, water is going to disperse in multiple directions with the force and eventually equate out into the volume it's sitting in. With a non-Newtonian fluid like cornstarch, if you were to slap it, it becomes like a solid. It will stay in its container in its current volume. and all of the energy is dissipated to the edges and falls off very rapidly. So some of the technology I used were software-defined radios, which are fairly new, that were created in the early 1990s. They allow an extreme amount of flexibility in radio design, testing, shrinks down our radios from the size of half that table to a box about yay big, just a few inches there. And then, of course, one of my favorite things to look at is wireless transmit of data. So the objectives, this project started as a class assignment for 1 semester only, and it grew. So, of course, the ideas, the expectations, they changed. So the beginning of this, I defined the objective, very specifically, to determine the relative permittivity of a non-Newtonian fluid. For those of you not in electromagnetics, permittivity is this idea of how much an electromagnetic wave gets attenuated as it goes through a medium. It's a derived unit that's based on lots of different measurements, but it gives us a really good idea of how a material can stop an electromagnetic wave. So the first idea that I had to solve this problem was to use SDRs and look at metrics of quality of service. So whenever you use Wi-Fi, you talk about quality of service, like how many packets are dropped in between here and somewhere else, and then goes to the internet, etc. You have an idea of quality of service. So that was an interesting idea, but it turns out it takes a lot of power to make it a few feet through a very dense subject. So other ideas had to be created, like the probe you saw there, which was also incredibly expensive, so I couldn't do that. And then moving on to waveguides, also expensive. So other ideas were created. I'll walk you through the application process. This entire research idea was inspired by the signal kinetics research group at MIT. They did work with UHF and sonar. So the idea is they wanted to communicate from a submarine under the ocean to an airplane flying in the sky, all in one wireless system with no base station on the surface. So they had to do a lot of electromagnetics and consideration of this transition from 2 fluid mediums, from air and water. They did this through, after a year and a half of study into that very specific transition, where the permittivities are incredibly different. This is on an order of like about 1.2 permittivity and 85, which is a loss of several thousand. Whenever we look at this, you kind of get an idea that it's important to understand the interactions between materials and electromagnetic waves. So that drove my research. So it turns out electromagnetics is a little complicated. Just a little bit. So waveguides are these ideas of structures that waves can propagate along one vector of transmission. And you ideally want this energy to be spread out throughout the cavity and moving through with phase. And that's what you see here. This is actually not animated in time, it's animated through phase of the electromagnetic wave. The first simulation didn't go so well. It turns out the length of the cavity is very important. If it's not long enough, energy does not transfer. So we fixed that. We spent a little bit of time working on it, fixing what's called the cutoff frequency. And it turns out my entire methodology worked for the waveguide experiment. Yeah. Man, it's a good feeling. But it's expensive. We only had half the system to do this, and it would cost too much to do the other side. So I needed to cut down cost. Instead of having copper, which is a really, really great conductor for waveguides, change that to aluminum. There's some loss, some benefit that I had to consider there, but surrounding this cavity, which I can't use the pointer, but on the outside is aluminum in order to constrain that wave, and it's incredibly important around those red rectangles that all of the energy from my antennas goes directly through it. So styrofoam is actually what I used for this experiment. Styrofoam acts just like air. It's got a permittivity of 1.02 compared to air. So to do the final experiment of putting these non-Newtonian fluids into different physical characteristics, I actually need to be able to measure through the cavity and measure how much power is transferred. So the first experiment is trying to get all of the distances, the variables of power, the amount of fluid that I can shake at a high enough rate to turn into a solid. All of that had to be figured out. So I chose oobleck, which is actually cornstarch and water in a very specific ratio, which takes a little bit of time to get just right. And I did back and forth measurements between air, just the styrofoam, with vibration, without vibration, different distances, did several partial factorial design of analysis of experiments, if any of you are familiar with that. And eventually it came down that a power level of negative 30 dBm, which to give you a scale in microwave radiation, your typical Wi-Fi antenna system that you see above you on the ceiling is usually around 0 dBm to 30 dBm. But at 2.4 gigs in this really close distance proximity, that's a lot of power at negative 30 dBm. And I can see all of the changes in medium with that power. So the final experiment, it takes some doing, trying to do it on a tight budget, but I have to have those antennas at exactly the same distance above the vibration table, and they must be the same distance apart and centered completely onto that cavity. So whenever I did this, I used a 2.4 gigahertz microwave system and pushed the electromagnetic waves through the cavity and measured the received signal on a spectrum analyzer. So you can actually, I believe I have a video on this. There might be sound, there might not, maybe, no sound. But you can actually see Faraday waves going across the surface of water. I didn't take a video of this with non-Newtonian fluid because I couldn't see it, but I knew it was happening because of quite a stark change in received power. So results. I wrote a paper on this, co-authored it with Dr. Who. And the great thing is we found that indeed the received power changes significantly with vibration. Whoa! Man, it's exciting. It's exciting whenever you get something right and it actually happens. So I can extrapolate this to a general conclusion that the permittivity of these fluids actually changes with vibration. I want to do a little bit more research on this before I get it published and submit it to a conference like the Texas Wireless Symposium and such forth, or the Gulf Coast Research Symposium. But I did submit it to the IEEE Region 5 student paper competition. So I'm in the running for that to go to the Region 5 conference and do a presentation similar to this under extreme scrutiny. But hey, that's fun. That's good. It's what researchers do. We like feedback. And a tidbit, I'll probably submit this to the LeTourneau Research Conference as well. So that's an invitation to y'all. If you're doing research, submit it, get feedback from people here in Longview and a wide variety of backgrounds. And of course, references. We don't want to get plagiarized. Definitely don't want that. So let me take a moment to kind of step away from the technical aspect and talk about REUs, because prior to last year at about the end of February, I did not know what an REU was. Didn't know it existed. And some of my friends in this room actually helped me realize these things exist. So I want to share a little bit of the aspects of this. I actually went over the summer to the University of Arizona, which is in Tucson in southern Arizona, and got to work in high frequency, which, to give you an idea, high frequency is not that high. It's just a name. What you just saw was what's called extremely high frequency, and the 2.4 gigahertz band like Wi-Fi. So this research goes all the way down to about 330 megahertz. So that's a factor of 1,000. Whew. And it gets more complicated because of that. So if you see on your left up there, that is my main research group in the electromagnetics and high frequencies. My mentor is there on the left, Noel Teku. And in the center there, you can see me and my research partner, Sierra San Roman, working with our HF monopole vertical antenna. And this is actually a group of about 20 student researchers from all over the U.S., some from Hawaii, Maine, Texas, Florida, one from Great Britain. So, you know, it's a great variety, lots of people to work with. I got to do some really, really cool stuff that was, in the essence, non-technical because it wasn't part of the research, but it was still fun. I got to work with really, really powerful SDR towards the end to do ham radio. I got my ham radio license through that, and worked with a local club to set up a new HF system with new antennas, couplers, things like that, balance, that will actually be used all across the state of Arizona for the National Weather Service. So there's fun to be had. There's opportunities you don't see. At the end, got to go and present at what's called the UROC conference, which is the University of Arizona's yearly exhibition of all scientific research. So wide variety like there is in this room. Scientists, medical people, engineers. It was a good deal. Tucson. Tucson is beautiful. Absolutely magnificent. It is also an interesting weather climate. It only rains for about a month and a half. And while I was there, it rained 2 times. And each time, the roads became literal rivers. All the water just drains to the center of the city with one giant riverbed that carries the water away. It's gone just like that. That picture actually is of a tornado. It did not touch down. I'm from East Texas. Whenever I see this, I run away. I go down to the basement. I already had my hand on the door going down to the first floor research labs. I'm like, I'm gone. And all the Arizona people are like, wait, I want to see it. Crazy people. It came down about 500 feet above the ground. It just stayed there, went over the city, and went back up. People just kept on driving. Wonderful. I got to go to a total of 7 museums. Man, museums are awesome. From optical science to actually getting to use a, I don't remember what size, telescope. But I actually got to use a telescope at a planetarium and look at Jupiter, some of Jupiter's moons, Saturn. It was a fantastic opportunity there. Different literary libraries there, like poetry, like not just your normal everyday library, mineral museums, great stuff. So an REU can be fun and technically challenging. That's the idea I'm trying to convey here. This research project had an objective that's pretty audacious, and we didn't meet it completely. But this is the idea. It would take about 3 years to do this project, And the idea was to create what's called a spatial temporal database of chirp soundings, and now so that we can analyze them and understand future conditions of the ionosphere, which I'll describe in a minute. And we wrote a paper on this. It is in the final stages of before publication. It's a long road, guys, the publication. It takes a lot of edits, some late nights, and especially collaborating across the country is kind of difficult. Chirp sounding. That's the first thing I should probably say. We call it chirp sounding, ionosons, things like that. I had a clip with a neat sound. I can try to make the sound. It sounds kind of like zoop. And it looks like that. It sounds like this little chirp that you hear. And ham radio operators are often like, man, I hear this all the time. I don't understand what it is. Why do I hear like this little tweet every once in a while? Well, the cool thing is that the National Weather Service, the Navy, and the Army have set up what are called ionosons that send out these linearly sweeping time-based signals that work all the way up through the HF band. They look just like that. They have a line that goes all the way across the spectrum in these little tiny discrete pieces. It sounds pretty useless at first. You're like, why? Why would I do that? The cool thing we can do with this, though, is we can actually understand the propagation characteristics of the ionosphere through this. So high frequency, why do we really care about understanding propagation in the HF band? Physics makes this possible. It's beautiful. Electromagnetics is beautiful. What happens is the highest level of our atmosphere, the ionosphere, actually takes these high frequency signals and bends them back down to Earth. It hits the ground, comes back up, bends it again. And you can actually send a signal around the world with only a little less than a watt if you have the right conditions. Again, I'll redefine the HF band. It's kind of important to know the numbers for that, 3 to 30 megahertz. And remember, we were working in gigahertz before to give you a scale. So what does all of this tell us? Whenever we do this analysis and we look at the reflections, we get what's called an ionogram. An ionogram has 2 axes and it's a 3D metric. So what you see in this picture is, on the bottom you have the frequency of reception with the virtual range of how high it is in the atmosphere, which again is a highly derived unit. It's a measure of group delay, distance. It's packed all into what we call virtual range. And so what we see is we can find out what frequencies are allowed to pass through and with what kind of delay they have. And so actually what you're seeing is that first signal around 15 megahertz getting lobbed off is getting retransmitted over and over again at lower and lower frequencies due to ionization. Why do we really care about this? That's the important question. The HF band is turbulent. And by turbulent, I mean I work in the HF band and ham radio, and in a span of 10 minutes, I can go from talking to someone to not being able to hear them at all. I wait about 10 more minutes, hey, it's back. I don't know about you, but that's not a great way to have a conversation. It's kind of hard. You have to hop around the frequencies until you can hear them again. This, it's not discriminating between civilian and military. The military has the same problem. They'll lose people whenever they're in the middle of conversations. It can be a really bad thing for extremely long distance, low power communications. So, what causes this instability in the ionosphere? It comes from both the sun, solar wind effects throughout our solar system, gravity, temperature inversions, differences between surface elevation. So ideas of scattering of electromagnetic waves around objects, the environment, mountains, things like that. So I have a cool graphic of solar wind at different points in our cycle. So right now we're in a really, really bad point of the solar cycle. It's very, very hard to transmit in HF. Okay, there it is. So the experiment idea. So it's a lot harder to transmit in HF than it is in microwave ranges like you saw before. For one, our antennas have to be really large. So you saw the antenna I was working with, it was about 4.5 inches, pretty small, easy to work with. This antenna is on the order of 6 to 7 foot. So we need a balcony, somewhere to work. Also, it has to be GPS referenced, so we have to be able to lock onto a time to be able to measure that group delay and derive virtual range. The setup we have is our GPS receiver and our HF receiver. They both go into what's called a software-defined radio, and that's where I can process all of this complex data and push it out to a computer. And then, I'm sorry, we use the same word in electrical engineering for the software-defined radio itself and the software-defined radio that is a program. So we call them the same thing, but on the computer, the software-defined radio can then analyze all of this data and turn it into ionosons and ionograms. So some of the cool things that I got to work with, this equation actually tells me when a chirp starts, what frequency it was at, and how fast it's moving. So since it is a linearly sweeping wave, I can actually figure out when it started, where it was at a certain time of the day, and what frequency it was at. And that's important. You've got to be exactly on this lock, or else nothing happens. You don't get a reception. And that's exactly what happens, problems. Whenever you deal with RF system, there's problems. Some were testing like in connectors, which are very, very large, very sensitive to alignment. That center conductor, whenever we ordered our first one, that center conductor, the gold pin in the middle and the top right, was approximately 3 micron too small. And it didn't make firm contact with the connector, and that took me a week to figure out. A good way to spend a life analyzing a connector and a whole system. Antenna troubleshooting. Whenever we didn't get a reception, first thought, antenna problems. It's blame the antenna. Well, electromagnetics people, we like to blame the antenna. It's fun. So brought in for the ham radio a massive dipole. That balcony, for scale, that is a tote about the size of this podium, and that balcony, it's taking up the entire balcony across it. So that idea, instead of being a vertical monopole, that's a dipole stretching all the way across a different electromagnetic phenomenon there. So it's the best reception you could possibly get. Unfortunately, we still didn't get the data we wanted. There's a problem in the program that we were asked to use that my partner is a CS major couldn't fix, and neither could I. So we ended up actually discarding our system for the moment that future years will actually use. And I reached out to the Australian government. They offered to give me a massive database of their ionosons. And so then I could turn all of that data into ionograms and then do cool stuff with it, like machine learning. You didn't know computer science was coming back in here? That's great. So the idea here is in an ionogram, there are two things that I'm really, really looking at. I'm looking at the maximum observable frequency, which is that far right asymptote that's sitting right about 17.2 megahertz, somewhere right in there. And then I'm looking at the lowest observable frequency, which in this case, we can receive down near DC, which is kind of cool. That doesn't happen very often. So this was excellent propagation characteristics. So what I did is to do data analysis and take apart all of these ionograms and come up with the metrics to describe them. From there, I wanted to do what's called regression learning, which is a simpler form of machine learning. It's kind of the baby of machine learning. It's the idea of being able to fit parameters to data. So if you took statistics, it's a lot like regression, except it's more complicated. Statistics comes back to bite you. You end up doing what's called kernelization of functions, so you're dropping higher order functions onto lower order functions over and over again to try to understand how far you need to move and to minimize your cost. So you see this in optimization and engineering, you see it in a lot of things like that. But I took it down to 2D, and 2D with, I think, 6 dimensions, and constantly flopping them back and forth to figure out where I'm going. So the results were very encouraging. The one on the far right is what happens whenever you don't tell it to plot one graph at a time. It can be fun. It's kind of hard to read and understand. I don't know about you, but I don't read squiggle. We actually came up with a realizable daily pattern. You're looking at the first pattern in the HF band that's ever been found. So that's really cool. Ham radio operators had often talked about it, but no one could ever prove it. And so we usually talked about around 10 o'clock and around midnight, 11 o'clock, the HF band is really, really good. I can use it all the way from around 28 megahertz to 2.5 megahertz. And of course there are some outliers, like 3 megahertz is usually pretty good all the time. All the time it's good. So it's really challenging to do this, especially in about a week of trying to learn machine learning well enough to see patterns. Especially this one was really interesting. I started to see a sinusoid that looks a great bit like the derived pattern in the end, even though it's not a sinusoid. So it takes some knowledge of what should come out to make a good regression. So where is all this going? In future years, so this will go for 2 more years, RU students will fix part of the broken program. Under my suggestion, it'll probably be scrapped and rewritten. So that'll be a good thing. They'll design an open database, so anyone can go and contribute to this. So the military can contribute, individual ham radio stations can put in data from places like WHISPER, which is autonomous HF propagation analysis. And as time goes on, these teams can build better machine learning algorithms to understand the ionosphere. And this will make remarkable progress towards reliable communication in this band. Right now, we have to take guesses. It's kind of difficult. We look up the solar conditions and make a rough estimation of, I think 5 megahertz might be a good band to work in today. Probably not. You're welcome to contact me if you'd like to work at RUs at the University of Arizona. They have opportunities in optics, medical sciences, chemistry. Really, really great chemistry program there. Optics was a blast, getting to see their telescope, fabrication facilities, different telescopes. It's a fantastic opportunity. And of course, more references, no plagiarism. And finally, we make it back to Laterno. Glad to be home, glad to be back here doing stuff. So I'm actually on the Legrand Senior Design team as a junior member. And this is a really, 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 really cool project. It's working with GPS, and it's funded by Sandia National Labs, which is a group that does cyber warfare, national defense, things like that. They do the dangerous stuff. So GPS, a little background into GPS because not everyone here is a double E and knows some of the background behind it. But we go from this idea of trying to drop bombs into mile-sized targets. Now that's pretty hard. I mean, you put on a blindfold and try to drop a bomb from 15, 20,000 feet and see how accurate you are. And now I have a cell phone about this size with an antenna, roughly the size of your camera's aperture lens here. And I've got a pretty accurate GPS position from the accuracy of from 2 classrooms down to where I'm standing. It's about the accuracy of this GPS. It's absolutely amazing. It's come through intense innovation in both hardware and software. So getting down to the idea of these GPS receivers used to be the size of this podium, a few foot tall, weighing about 120 pounds, and sitting in a server rack with a power unit outside. It's pretty hefty. To a software-defined receiver that's sitting in my lab that's about a foot by a foot, and it can do anything I want to do. It's pretty amazing. However, even with all these innovations, new satellites being launched, better signal integrity, by the time the signal gets to Earth, it's sitting at around 10 femtowatts. That's pretty rough. Whenever it's being sent, it's not being sent at a weak power. It's sent at about the wattage of a efficient light bulb. The problem with this is once it gets down into the area where we can use it in the lower level of the atmosphere, it can just be absolutely destroyed by jammers, which I can unintentionally say, yeah, I have done that before. I don't recommend jamming your GPS in a closed-off lab. Not a good idea. But it's fairly easy. It doesn't take much. The other idea here that makes all of this very difficult to work with is the FCC regulates the use of GPS very, very, very tightly. You cannot transmit on the GPS band. You will go to jail. So we need ways to study how to stop jamming and what we call anti-adversarial attacks. So that's where this project comes in. We're trying to figure out a way to build a test range in a different part of the frequency band. So GPS is at 1.5 gigahertz. That's back in the microwave band that I talked about before. And we want to take this down and put it into the millimeter wave band around 900 megahertz. If you have any familiarity with Wi-Fi and Bluetooth and things like that, you've probably heard of what's called the ISM band. That's an open part of the spectrum that anyone can use at low power. And then ham radio operators can operate at high power there. What we want to do is be able to do these attacks on GPS signals in that band, where they look almost identical to GPS, but we can actually attack them, take them apart, try to figure out how they propagate through space. So we come up with this idea called pseudolights, which take in the real GPS signals that are swooping by the Earth, just zipping around. And they take that and they turn it into our 900 megahertz signal, and they push it out from different physical locations to a centralized receiver. This receiver takes in both the real signal and our emulated signal and comes up with models about how accurate our signal is and how well we're doing in emulation. That's the first year in what we're working on, creating these pseudolights from hardware from UT Austin, and then changing it and then redesigning our transmitter to be our custom design so that all of this can work together and emulate GPS. In the future, this will be a 3-year project, so we have 2 more years. This is where grad research and senior design for you upcoming juniors and sophomores and that idea can actually get involved, because we have to be able to create these spoofing algorithms based on research papers. A lot of these papers talk about the theory, they do a small experiment, and they move on. And they usually have to get onto a super yacht and go into the middle of the Mediterranean to do it so that they don't go to jail. The idea that we'll have for research is we'll do both location estimation, angle of arrival estimation, and then we'll look at creating these signals in real life in these attack scenarios. So there's kind of a wide variety of people we need. We need CS, we need all sorts of engineers to understand how we build out our system, from mechanical and electrical we really need. We have to understand how we can build these systems, move them, keep our signals stable. So it will be a really, really cool project to continue for the next 2 years. And with that, I'll take any questions on any of the 3 projects or research, REUs. Any questions?
What does REU stand for again?
Research experience for undergrads. Thank you, you caught me.
How many REUs do you need to apply to?
That's kind of a fun thing. People that know me know how this happened. That in late February, I was introduced to this idea of an REU, turned around, applied for the first one, and got it within a week. So it's kind of cool, but I don't recommend doing it that way. I would probably apply to at least 3 to kind of get a good spectrum. I would apply to a few different ideas of what you want to do. You could go to the NSF website and do a parametric search to find out all the different kinds of programs they have. Any other questions? Yeah.
Yeah, for your non-Newtonian fluid, like how did you end up like oscillating like at a high enough?
Actually, I worked with the civil department on this and borrowed a concrete shaker. So that's about a 75-pound device that's, I'm trying to think, that's probably 3 foot by 3 foot. Just this massive device, rolled it into the electromagnetic lab, and set that experiment up. You can see, I can probably go back here. It's not too far. 3. And so I actually used that concrete shaker. Oh, it skipped. My bad. And that platform is actually shaking that styrofoam container at a high enough frequency and amplitude to change the phase of that fluid. So in water, it just creates Faraday waves and these different harmonics that you can see. And I played with it. I had some fun. Amplitude is it's a function of both amplitude and frequency. So it's all sorts of fun. I didn't have control over frequency, so I would much rather have a higher frequency and sacrifice some amplitude, but in civil engineering, they don't care about either one. They care is it moving. So that's all right. It's all right. I'm very thankful and glad I could use it to work on research. Any more questions?
Which of these 3 was your favorite and why?
Man, that's a tough question. I'm probably going to say, it's hard. I'm gonna give the answer to the high frequency REU, just because I got to have a very large spectrum of ideas to work with. I had a lot of freedom. It's basically becoming a PhD student for 10 weeks, which is a fantastic experience. You get to see what it's like somewhere else, especially if you go to a secular university. You get a diverse experience for sure. That's to say the least. I think we're about 5 minutes. 5 minutes or
Any other questions? Okay. If not, remember, Sarah Bittner will be here next week. Talk about chemistry, ethics, and we have lunch at the Corner Cafe here after our seminar. And let's thank our speaker one more time. All right, we'll see you in the joint room on the Corner Cafe. Thank you.
Okay.
What was this out here?